Alright, hello. So let's take a look at integration. So when I started the series calculus, I mentioned that calculus is about two things, A, the differential, and B, the integral. We looked at differentials, which had to do with gradients. So now we will look at integration, which has to do with areas under the graph. So let's take a similar situation. Let's say there's some car at some point X, and that car speeds up and then slows down, right? So what I want to do is I want to plot its displacement time graph, right? And if the problem that you would find in this goal is that the velocity at every point is changing. So just a recap, velocity is the change in displacement over the change in time. So the change in displacement is velocity at that point multiplied by the change in time, right? But the problem is that velocity is changing at every point. So it would be a hard task to do. So let's say what you do is that you take intervals of 1 second, and after every 1 second you plot its velocity at that point, right? So 1 2 3 4 5 at t equals 0. When you look at the speedometer, it says 0 because it's at rest, the car is at rest, so you put a line there. And then from 1 to 2, let's say when you look at the speedometer, it gives you the value 1. So you put a line there. And from 2 to 3, it gives you a value 2. Put a line there. From 3 to 4, it's back to 1 as it is slowing down. And at 4 to 5, it's 0 as it has come to rest. Right. So if I want to find the change in display, if I want to plot the displacement time graph and I know that it's initially at 0, if I know the change in displacement, how much it is changing, right? I can simply, I would be able to know how the displacement time graph looks like just by knowing that how much it is changing, given that I already know that it's initially at 0. Right. So the change in displacement can be found out by multiplying these two values, and multiplying these two values is can be interpreted as finding the area of a rectangle such that its length is v and change in t, because the area would just be v multiplied by the change in t, right? So this is just one way of interpreting it. So if I drop lines over here, I would be completing these rectangles, right? And if I find the area of these, I would be finding the change in displacement. So from 0 to 1, the area is just 0. So from 0 to 1, S did not change, 0 to 1, right? And then from 1 to 2, this area would be 1 because this much is 1 and this much is also 1. So from 1 to 2, my displacement changed by one value. So from 1 to 2, it increased this much, right? And then when I look at 2 to 3, it increased by a value of 2. So 1 plus 2 would be 3, and it would be something like this, right? And then continuing 3 to 4 would increase the value by 1 again, and then 4 to 5, the area of that rectangle is 0, and so we achieve a straight line again. Right. But the problem here is that you are generalizing it a lot, because in real life it's not the case that from 0 to 1 the car is at 0, the velocity of the car is 0, and then from 1 to 2 it magically jumps to 1, and then from 2 to 3 it magically jumps to 2, and so on. Right? That's not the case. So let's say in order to make your experiment, in order to make this a bit more fair, what you do is now instead of taking 1 second changes in time, what you do is you check the speedometer after every 0.1 second, right? And then you're noting down its velocity. So if you try to join the lines, of course, you would get something like this, right? The velocity is increasing, reaches some sort of a maximum over here, and then it continues to decrease, right? So now once you try to plot the change in displace the displacement time graph by just finding out the areas up to that point. So for example, if this is t equals 2, right, and t equals 2 over here, what I would be doing is I would be taking this area, this area, this area, this area, this area, adding them all up, and the value it gives me, that will be my value of displacement. Right, so if I try to plot my displacement time graph using this information, what I would get is some small lines that are changing like this, right? And they're joined. Okay, so something like they're joined, right? So when I compare my two models, one where I took huge jumps, huge steps of 1 second, and the one where I took a finer step of 0.1 second, what you realize is that this second model is a closer and fairer representation to what it actually might be. Right, coming from the first video of calculus, we know that under this situation, the velocity time graph would look something like this, and the displacement time graph would look something like this. Right. So the takeaway from this is that if I take smaller changes in x, in this case x is time, if I take smaller changes in time and I am finding the area up to that point, it is it is a close representation of the actual displacement up to that point, right? So as I'm decreasing my change in time, as I'm taking finer and finer steps, and I am taking all the areas of the rectangles up to that point, the value that I get of or the sum of areas would be the displacement up to that point, right? And this approximation gets better as my change in x approaches zero, right? Just looking at this graph over here, if I want to, so displacement is just the area under the graph up to that point. Okay, so area up to the graph at that point, simply because the change in displacement is velocity at that point multiplied by the change in time. So the displacement is really the velocity time graph is the area under the curve for the velocity time graph. So if I can break up this graph into small and small rectangles, right, and I'm finding the area of that rectangle simply because I know how to find the area of that rectangle. I could get the area simply by adding up all the areas of rectangle, right? You might argue that at some points there's extra area being added, and at some points there's some area being left out. But as I am taking smaller and smaller changes in time, or as my rectangles are getting finer and finer, this approximation is getting closer and closer to the actual area under the graph, right? Because these extra areas and the areas that are left out would be getting smaller and smaller as I'm taking smaller steps, right? And so this is what an integral is. The integral would be the area under the graph up to that point. So another way of looking at integrals is actually in terms of differentials, right? So if there's some function f of x, and let's say I differentiate it and it gives me some other function g of x, integrating that function g of x will give me back f of x, right? Because differentials and integrals are opposite or inverses, right? So in this case, we took example of displacement time and we took example of velocity time, right? And we know that the differential of displacement time gives me velocity time, and so the if I integrate velocity time, it will give me back displacement time. Right, but differential gives me the slope and integral gives me the area. So how are these connected? Right, so let me draw a rough sketch of these. Right. So if I take a look at t equals 1, right? If I take a look at t equals 1, the way I got this certain value, the way I got the value of v when t was 1, was that at 1 there's some displacement s, and then I took some change in x, so some small change in time, right? And it gave me some small change in displacement. The way I got to this certain value of v is that I took the change in displacement over the change in time at the instance when time is 1. So ds dt when t equals 1, right? This is whatever value this is, it's the value over here. Right. Again, V is change in displacement over change in time. So the change in displacement is V multiplied by the change in time. Right. So let's say now I take some small change in time over here, and just remember in mind that this small change in time is in principle a very, very small change. So if I complete my rectangle over here, let's take a look at what this area gives me. So ds dt at the point when t equals 1, if I multiply this by dt, that just gives me the change in displacement when time is equal to 1. Right, so if I integrate ds dt multiplied with dt, it should give me integral of ds. This integral sign, it just means sum up, right? So it just means adding all of those. So in this case, if I rewrite this as v dt, if in this case what it really means is that all of these triangles that we got, you multiply all of these rectangles, sorry, all of these rectangles, you sum up all of their areas, right? This means sum, and this multiplied by this can be interpreted as this area, and so integral of this really just means adding up all of those areas, right? And so if let's say I know how much s is changing. I know at initially it's at 0, and I know how much it's changing. So if I sum up all the changes, it will give me the final output, right? It will give me s in short. So the integral of ds is just s, because you are summing up all the changes that have happened, and initially it was at 0. So all the sum of all the changes in s that happened will just give me s, right? So this sort of makes sense why integrals and derivatives would be opposite, right? Because here, if I did not convert it into v, the v could be written as ds dt multiplied with dt, right? The v is actually the differential, so the t's and t's would cancel, and this is why these would be equal, right? So s would equal s. Right. One way of looking at this dt would be that you are integrating v in terms of t. Right, so because v was actually the differential of s, when we integrated v in terms of dt, it gave us back s, and this is how derivatives and integrals are linked together, and so you can define integral to be some function f of x, you can define integral of g of x to be some other function f of x, such that when you differentiate it, it gives you back g of x. Right. So that's all for today. And in the next video, we will be looking at how to exactly compute these derivatives, how to come up with the functions, right? Till then, bye bye.